So in the lessons for quantum computing, one experiment that we learned about was the double slit experiment. And one key feature of the double slit experiment that we talked about was when we added an observer to see which slit the quantum particle went down, it changed the results that we saw on the final detector. So to revisit the double slit experiment, we have our electrons that are being shot out and aimed at the screen that has two very small slits in it. This is going to create a wave-like pattern that, when hitting the final detector, creates this interference pattern. However, one thing we talked about was that if we add an observer to see which slit each electron went down, the detector ends up losing that interference pattern that we saw earlier and acts more so like a classical particle going through the slits. This is of course due to the fact that the quantum particles were in a superposition of either going down one slit or the other, and observing the particle destroys that superposition. In this experiment, one main question that has been brought up is how we could bring back the impossible. This is essentially what the quantum eraser tries to achieve. So in order to set up the quantum eraser, we have to adjust our double slit experiment. So we still have the same setup with the source of the quantum matter. In this case, I'm going to be using photons since that is what's commonly done with the quantum eraser experiments. And these photons go through the two slits here. Whichever photon comes out, the red one or the blue one, will hit this. This is crystal beta barium borate, and what this crystal does is essentially make two entangled photons. So in this case, the two red photons here would be entangled together, or the two blue photons would be entangled together. And then we get to the last part of the quantum eraser that follows the original double slit experiment, which is that one of the entangled photons is going to be directed at this counting detector, often called D0. And so it's going to hit the counting detector, and with this detector, we are going to observe which slit the photon came from. So this of course is going to make the detector at the end to lack that interference pattern that we want to see. So now we look at what happens to the second entangled photon. Depending on whether we have a red photon or a blue photon, it's going to hit one of these two beam splitters. And what this beam splitter will do is that it'll have a 50% chance of transmitting the photon, which means it'll hit one of these two detectors, D1 or D2, depending on which slit the photon came from. Or it'll be reflected, and it'll be reflected to either D3 or D4 here. And so knowing that the only photons that could be reaching D1 are the ones from the red slit, and the only ones that could be hitting D2 are from the blue slit, it makes sense that when we look at the results of the detectors, that D1 and D2 are going to lack that interference pattern. However, since we have a random chance when the photons are reflected of hitting either D3 or D4, no matter which slit the photon came out of, this means that the results of D3 and D4 are going to show this interference pattern, because in essence, the knowledge of the path that the photon took has been erased, thus achieving the quantum eraser that we're looking for. So we've erased the knowledge of which path the photon took. That means that D0 is going to show that interference pattern that we want, correct? Well, we'll get back to what really happens in this situation later, but let's entertain the thought that D0 does return to that interference pattern. Wouldn't that be some kind of time travel in a sense? Well, one topic that the quantum eraser brings up regularly is this idea of what's called retrocausality. And what I mean by retrocausality is a case where a future action affects the past, which seems kind of paradoxical, but we'll see in the next example how this idea can be used. So if we go back to the Schrodinger's cat example, we have a cat that's in a box, and we put a radioactive material that is controlling a vial of poison in the box. So while this radioactive material decays, we're not sure if the cat is dead or alive until we open that box back up. However, let's say that we do open the box, and we see that the cat is alive. Typically, from this example we have learned about, we understand that when the cat is in the box, before we know its true state, that it's in a superposition of being both dead and alive. And that superposition is destroyed as soon as we open the box and look inside. However, if we adopt the idea of retrocausality, then it could be argued that the cat was essentially alive the entire time, and that the action of us opening the box affected the past state of the cat, cementing it as being alive. This would mean that the process of the cat's state changing would evolve backwards. So with this idea of retrocausality, many people have come to the idea that the quantum eraser essentially takes the past results of the first detector and then changes it to show an interference pattern based on the future actions of erasing the information of which path the photon went down. However, this is actually a misconception and not how the quantum eraser genuinely works. To get back to that first detector that we had, What really occurs after the quantum eraser has erased the knowledge of which slit the photon went down is that a comparison is made between the two detectors showing interference and the original detector. Remember how with the original detector, we did make an observation of which slit the photon went down, so we should in theory know the position of every photon that had its information erased, since the entangled photon that hits one of the four detectors is hitting that detector mere nanoseconds after the other entangled photon has been counted on the initial detector here. With this information, we're able to extract the data from that first detector, and when we find each photon that had its path erased, then we are able to observe that interference pattern. So this experiment is really more of an example of quantum entanglement. But what about superposition? Could the experiment work without superposition? In more specific terms, could the quantum eraser work with photons in a mixed state versus in a pure state? While the setup for this experiment is slightly different to account for creating an interference for the photons in a mixed state, the results between both the mixed state and the pure states are strikingly similar. This includes seeing an interference pattern or a lack of an interference pattern on each of the respective detectors. However, one major difference between the two examples is the results for the counts of each experiment. To go further in detail, if we were to add a coincidence counter, or in this case, a counter that counts each time the first photon hits D0 and the second photon hits any of the other detectors, we would see the same results from both the mixed experiment and the pure experiment. However, if we were to obstruct one of the slits at the start, we would notice something interesting. The pure state experiment would act as we'd expect it to, only showing coincidence counts for that slit that is uncovered and showing none for the obstructed slit. But when we look at the mixed experiment, the amount of counts for the unobstructed slit is half of what we would expect. The reason for this is that in the experiment with the mixed states, the photon is not actually going down one slit or the other, but rather going halfway down each slit. This would in turn mean that any count for a single slit would be half a count, thus reducing the final results. This reflects exactly what we see with qubits when we have a mixed state and a pure state, regardless of how the experiment is performed. The main quality of quantum mechanics that's highlighted is the entanglement observed between the photons as they are detected. While this entanglement defeats the notion that the eraser implies retrocausality, the experiment offers insight into how quantum matter acts upon observation or the reversal of such. When it comes to the quantum eraser, we get to look further into the quantum world, specifically when it comes to entanglement. Is there a practicality to the quantum eraser experiment? Not necessarily. However, if we look back to the double slit experiment, we see that the results of both the quantum eraser and the double slit are very similar, and that they more so teach us about the quantum world than have any practical use. When it comes to the double slit experiment, we're introduced to the notion of superposition when it comes to the interference patterns that we observe, especially when it comes to the fact that an observance of the superposition causes it to collapse. And this allows us to both observe which slit the photon went down, as well as see the interference pattern at the end. As mentioned, this doesn't necessarily have a practical use, but is very important when it comes to understanding the qualities of quantum mechanics, and can mainly be used as a catalyst in which other areas of quantum mechanics can thrive off of.